Hello everyone, today I'll be discussing the paper DCFace, Synthetic Face Generation with Dual Condition Diffusion Model. This research was conducted by the following authors, and the work contributes to the understanding of synthetic face dataset in relation to face recognition models. Let's go through an overview of this paper. It presents a generated face dataset that undergoes a two-stage generation process. Firstly, synthetic images of new subjects are created using unconditional diffusion models. Secondly, style reference images are sourced from a collection of real images. Finally, these two conditions, subject identity and style, are integrated to create new images. In these images, the identities derive from the synthetic subjects, while the styles are taken from the real images. The primary focus of the paper revolves around analyzing the diversity and consistency within synthetic datasets, and we control these aspects through the use of a dual condition diffusion model. The key characteristic of a desirable synthetic dataset include consistent identity and large diversity. A real dataset can satisfy these conditions if it's free from label noise and derived from a variety of sources. When face images are generated using unconditional generator, control over the subject ID is lost, resulting in label inconsistency. Previous methods like GAN-based generators can attain high label consistency. However, these models often struggle to produce diverse styles of images comparable to those found in real datasets. Moreover, a high-quality dataset should also contain numerous unique subjects. We propose a dataset generation scheme that can effectively control both label consistency, diversity, and number of subjects. In order to generate a face dataset, we utilize a two-stage generation pipeline. Firstly, we create a facial image using an unconditional DDPM trained on facial images. Empirically, we demonstrate that DDPM is a better suitable choice for this task than GAN, as DDPM can generate a greater number of unique subjects. Subsequently, we select a real image that will serve as a style reference for the generated image. This image is chosen from a predefined style bank, which can consist of an arbitrary set of real facial images. Then in the second stage, we combine the identity image and the style image. However, given that we lack a ground truth image as a learning target, this task is far from trivial. The crux of learning a generator lies in ensuring that the generated image inherits its identity from the ID image, XID, and its style from the style image, XStyle. In this study, style is defined as any visual features that don't contribute to determining the identity of a subject. On the one hand, if the generator relies excessively on XID, it will fail to produce diverse images. In the worst case scenario, the generator will always simply mirror XID, rendering it useless. On the other hand, if the generator overly depends on the style image, it risks losing the subject's ID. This implies that the generator fails to maintain the identity of the synthetic image when the style image is replaced. The solution we propose involves striking a balance between these paths using an information bottleneck structure. Initially, we create a training dataset by selecting two images of the same subject. We then designate the style image as a target image. For the style image branch, we design a style extractor to prevent fine details from entering the generator. This extractor eliminates high-frequency details by spatially pooling the image into a vector, a technique inspired by StyleGAN and others. To retain some spatial information, we perform spatial pooling, but at a patch level. The granularity of the patch controls the amount of information from the style branch and facilitates the balance between consistency and diversity. In essence, we are fusing the identity image with the destroyed style image to predict the target image. Once the generator has been trained, we can take XID and XStyle from different subjects to predict the new image. This image inherits its identity from XID and its style from the XStyle images. If we repeat this generation process multiple times for each identity image using various style images, we can construct a label dataset. At the bottom, we've displayed some images with distinct identity and style images. Recall that DCFace effectively manages the trade-off between diversity and consistency by adjusting the patch size within the style extractor. As illustrated in the figure, we observe that a decreasing patch size from 7.5 to 3 results in a decrease in diversity but an increase in consistency. Among these options, the optimal choice is a patch size of 5. Furthermore, we compare our result with previous works such as DCFace and CVPR, which exhibit a high ID consistency but limited diversity. The size of a circle indicates the accuracy of face recognition model trained on the respective datasets. We conducted experiments using different training datasets for face recognition models, including a real dataset called Casilla Web Face, CVPR based on GAN, DCFace based on 3D models, and our own method utilizing dual condition diffusion models. By exclusively using synthetic images, we demonstrate that DCFace is capable of training a superior face recognition model, which performs well on validation sets containing real images like LFW, CPLFW, and HDB. Although the model trained on the real dataset still outperforms it, the performance gap has been significantly reduced. In addition, at the bottom of our result, we present the performance when training a model using a fully synthetic dataset larger in size than the real dataset. With the increased dataset size, we observe an improvement in performance. However, the model trained on the real dataset still retains the overall advantage. Lastly, we demonstrate that different synthetic datasets can be complementary. By combining DCFace with the DigiFace 1 million dataset, we achieve an improvement in performance for the fully synthetic dataset, reducing the performance gap to the real dataset by an average of 1.6%. For more detailed information and comprehensive experimental results, please refer to the paper. We also have made the code and dataset available in our GitHub. We encourage you to visit our GitHub repository for further exploration. Thank you for your consideration.